Welcome to the deep dive. Today we're diving headfirst into particle physics.
Exciting.
You sent us this research paper,
Yeah.
and it looks really interesting.
It is.
So we're going to try to unpack it together.
Sounds good.
And it's called Electroweak Corrections and EFT Operators in W plus W Production at the LHC.
Catchy title, right?
Very catchy. Rolls right off the tongue. So, in a nutshell, this paper is about scientists using massive experiments
Huge experiments.
to try and figure out what we don't know about the universe.
It's like they're searching for clues about new physics.
Like what kind of new physics?
Like hidden rules and particles that could totally change our view of the universe as we know it.
Okay, so kind of like a fundamental shift in our understanding.
Exactly. And they're doing all of this using data from the Large Hadron Collider, you know, the LHC.
Oh yeah, I've heard of that.
It smashes protons together at ridiculous speeds.
Protons?
Yeah, like super tiny particles.
Okay.
And when they collide, it creates this shower of other particles.
So like we're trying to smash these protons open to see what's inside.
Basically, it's like we're trying to recreate the conditions of the Big Bang
Wow.
to understand the fundamental building blocks of the universe.
That is a lot of data, though.
Oh, it's an insane amount, like an avalanche of information.
So how do they even begin to make sense of all that?
That is where effective field theory, or EFT, comes into play.
EFT. Okay.
And this is where it gets really cool. Imagine you're watching a shadow puppet show.
Okay, I like shadow puppets.
Right, but you can't see the actual puppets, only their shadows on a wall.
Oh, yeah.
EFT is like analyzing those shadows, their shapes, and how they move to figure out what those hidden puppets might look like.
So instead of trying to see these new particles directly,
Which is really hard.
they're looking for how these particles might be affecting what we can see.
Exactly. It's a way to find clues without knowing exactly what we're looking for beforehand.
That's really cool.
Right. And within EFT, there's something called SMEFT.
Chess T.
Yeah, it stands for Standard Model Effective Field Theory.
Okay, that makes sense.
Imagine our current understanding of physics, the standard model, is like a giant jigsaw puzzle, right?
Gotcha.
SMEFT is like adding a few extra pieces to that puzzle, representing the potential effects of this new physics.
And are those extra pieces what scientists are looking for in the LHC data?
You got it. They're called higher dimensional operators. They're like placeholders for what we don't yet know.
Don't worry.
And by analyzing how well the data fits with or without these extra pieces, scientists can test different hypotheses and hopefully find evidence of something truly groundbreaking.
So we've got our puzzle, our potential extra pieces, and a machine that smashes particles together to give us clues.
Yeah.
Where does this paper fit into all of this? What puzzle piece are they focusing on?
This is where it gets even more interesting. This specific research zeroes in on one particular process, the production of a W plus WR boson pair.
W bosons. Remind me what those are again.
Sure, W bosons are fundamental particles.
Okay.
And they play a crucial role in the weak force.
Okay. And the weak force is?
The force that governs things like radioactive decay.
Got it. So we're talking about some pretty important stuff here.
Extremely important.
Why focus on this particular process, this W plus W production? What makes it so special for this search for new physics?
So this W plus W production, it's like a keystone to this whole particle physics arch, you know? It's directly connected to how particles gain mass, which is huge.
Right, because mass is kind of a big deal in physics.
Kind of. It's everything. And we think we have a pretty good grasp on it, right? At least that's what the standard model tells us.
Okay, so that's our baseline, right? Like what we should see at the LHC if everything is working normally.
Exactly. So any deviation from that prediction, even something super small, could be a big sign that something new is happening.
Big flashing neon sign.
Exactly. And within this W plus W production, it gets even better because we can see how these W bosons are polarized, which is kind of like their spin, how they're oriented.
Their spin.
It's more complicated than that, but you get the idea. The point is, some combinations of these polarizations are more likely to be affected by those new physics effects than others.
So we've got our W bosons, we're checking their spin, and we're hoping to see something unexpected. How do scientists actually go about doing that?
Well, this is where the magic happens. They build a virtual universe inside a computer.
Wait, what? Like a simulation?
Exactly. They create unbelievably complex simulations of these particle collisions, and they run two main types. First, there's the control group.
Yeah, okay.
They simulate the W plus WI production based solely on the standard model, no new physics allowed. That's their benchmark.
Gotcha. Business as usual. What's the second simulation?
This is where it gets exciting. This time, they take that same simulation, but they add in those SMEFT operators we discussed earlier, those placeholders for new physics. Then, they compare the results side by side. Any difference, any discrepancy, could be a sign of something new.
So they're basically looking for a subtle flicker in the data, a sign that the rules are different than we thought.
Exactly. But of course, it's not quite that simple.
I figured as much. Real life is never as clean as a simulation.
You said it. Those simulations have to be incredibly detailed to take into account all the tiny factors involved in an actual particle collision.
Because even a tiny mistake in the simulation could throw off the whole thing, right?
Exactly. It's like that old saying, garbage in, garbage out. If the simulation isn't accurate, the results won't mean anything.
So how do they make sure these simulations are as realistic as possible?
Well, that's where Electroweak corrections come in. Remember those from the title?
How could I forget?
They're a big deal. Imagine you're trying to calculate how far you can throw a baseball.
Okay, I like baseball.
You'd probably consider things like the angle you're throwing at, how strong you are, stuff like that, right?
Right.
But for a really accurate prediction, you need to think about air resistance, the wind speed, even how the ball is spinning. Electroweak corrections are like all those extra details, but for the world of particle physics?
Okay, so it's about making sure every tiny detail is accounted for so the scientists aren't fooled by something that's not actually new physics?
Exactly. It's about making sure the data they're looking at is as clean and accurate as possible so the results are meaningful.
So they've got their simulations, and they've added in those Electroweak corrections. What did they find?
Are you ready to find out?
Lead the way. Did they find evidence of those shadow puppets dancing to a new tune?
Well, not quite.
Oh,
They didn't find conclusive evidence of new physics in this particular study.
so does that mean it was a bust? All that work for nothing?
Not at all. It's like, even though they didn't strike gold this time, they learned a ton about where not to look next time.
So it's more about refining the search itself?
Exactly. It's like they've sharpened their tools and honed their methods.
Okay, so what did they find out? What are some of the key takeaways?
One of the biggest surprises was how much of an impact those Electroweak corrections had. Remember the tiny tweaks to the simulation we talked about earlier?
Yeah, like fine-tuning a telescope.
Precisely. It turns out those corrections are crucial for getting a clear picture of what's really going on in the data. Like, they can drastically affect how we interpret the results.
Really? So those tweaks weren't so tiny after all.
Nope. It's like, imagine you're looking at a blurry photo
Good.
and you adjust the focus just a little bit.
Right.
Suddenly you can see all these details that were hidden before. That's what these Electroweak corrections do for us.
Wow, that's incredible. So in a way, these Electroweak corrections, they're both a blessing and a curse, right?
Yeah, right.
They make the simulations more accurate, but they also add another layer of complexity to the whole thing.
It's true, but that's what makes this research so exciting.
How so?
Well, it's not just about finding new physics, it's also about constantly pushing the boundaries of what we know and how we know it.
That makes sense. So where do we go from here? What's the next step in this cosmic scavenger hunt?
Well, this research focused on just one particular way of analyzing this W plus W wave production, right? So maybe there are other approaches, other ways of looking at the data that could reveal something new.
So we need to get even more creative with our methods.
Exactly. We need to think outside the box, challenge our assumptions, and keep searching for those hidden clues.
And hopefully, with enough digging and with those refined tools, we'll eventually uncover those extra puzzle pieces.
Who knows? Maybe those shadow puppets are just waiting for us to shine the right light on them. And when we do, it could change everything we thought we knew about the universe.
It's like that saying, the more you learn, the more you realize you don't know.
Exactly. And that's what makes this whole journey of scientific discovery so exhilarating and rewarding.
Okay, so back to the big question. Did they find those shadow puppets or what? Did our scientists uncover those extra puzzle pieces we were talking about?
Well, in this particular study, no, they didn't find conclusive evidence of new physics. But that doesn't mean it was a failure or anything.
Oh, okay. How come?
Because they learned a ton. It's like they were searching for buried treasure. And they may not have found the treasure chest this time,
Right.
but they learned a lot about the lay of the land.
I see. So it helps narrow things down for future searches.
Exactly.
Okay, so what are some of the big takeaways from this research then?
Well, one of the most interesting findings was how impactful those Electroweak corrections turned out to be.
The tiny tweaks to the simulations.
Yeah, those little tweaks turned out to be way more important than anyone expected.
Really? But how?
Well, it turns out that even tiny inaccuracies in those simulations can really snowball,
Mhm.
and it can make the data look like something it's not or hide the signal you're looking for.
Oh, I get it. So it's like you might think you've spotted a rare bird,
Right.
but then you realize it's just a common pigeon with weird lighting. Those corrections help us see clearly and avoid those kinds of mistakes.
Exactly.
That's fascinating. So, in a way, this paper was just as much about refining our methods as it was about finding new particles, right?
Yeah. Precisely. And that's the thing about scientific discovery. It's not always about making a huge breakthrough in one go.
It's about the journey.
Yes. And constantly refining our tools and techniques along the way so that we can keep asking bigger and better questions.
That makes sense. So, for our listeners out there, what's the one thing you hope they take away from this deep dive?
I think the biggest takeaway is just how much dedication and ingenuity it takes to do this kind of research. These scientists are pushing the boundaries of what we know and how we know it, and even when they don't find exactly what they're looking for, they're constantly learning and refining their methods.
And maybe, just maybe, with enough digging and with these super precise tools, we might one day unlock those secrets of the universe.
Exactly. The journey is far from over. There's still so much out there to discover.
That's an exciting thought. Thanks for joining us for this deep dive into the world of particle physics, and a huge thanks to our expert for breaking down all this complex stuff.
It's been my pleasure.
Until next time, keep those minds curious, and we'll see you on the next deep dive.